In your project number 3, you are asked to implement the binary search tree through one-dimensional array. Instead of implementing it through the regular linked list, which of course we have discussed in our lab, one-dimensional array has some magic to actually create a binary search tree and be able to work close to perfect. Let's take a look of how is that possible. So for a binary search tree, is a binary tree which every node satisfies the following things. All the nodes on the left subtree is smaller and all the nodes on the right subtree is larger. So it is totally possible to create a binary search tree without using pointers. So let's take a look of a simple example of this one. Say now we create a one-dimensional array with size of 8, as you can see in this simple example. We will start to use index of 1 instead of 0, and you will understand why pretty soon. Saying that these are the data that we store in a one-dimensional array, of course, it doesn't look like a binary search tree at all. It doesn't look like even a tree. However, if you try to project that into a binary search tree structure, you actually will be able to see a binary search tree stored in a one-dimensional array. Starting with index of 1, you can see that we put 5 over here. That's corresponding to the root is actually 5. For the next location, from top to bottom order, left to right order again, you can see that the next child on the left side is given as index of 2. The right child of that is given as index of 3. In this case, you will see that when we put 3 over index of 2 is actually indicating that 3 is the left child of the root and 8 is the right child of the root. And if we keep going, you will see that index of 4 and 5 holds the left child of 3 and the right child of 3. And if that is no child, we specify it as a null value, indicating that this one does not have any values in this node, which is exactly the same idea that we have in the binary search tree. So if you dive into this structure, you will find the corresponding things between the one-dimensional array with the binary search tree. So you can see that starting with array index of 1, for any node to find its parent's index, all you need to do is using the index divided by 2. You don't even actually need to distinguish the index is even number or odd number, because if we use integer division, -1 or not -1 does not matter at all. More importantly, if you try to find your children's index, all you need to do is you multiply your own index by 2, then you find your left child's index. Let's take a look of the root. The root is here. If you're going to look into your left child index, you multiply by 2, which is this one, 1 to 2. You see the left child of index of 1 is at index of 2. If you try to find the left child of this index, you will find that it's going to be 2 multiplied 2 equals to 4. Of course, if node 1 has one more left child, it will stay at index of 8. For the right child, because the right child is one index apart from your left child, so it will always be index multiplied by 2 plus 1. Therefore, if you try to look this node index 7, which holds the value of 9, if you try to find the left child, if there's any, then the index would be 14 on the left child and 15 on the right child. So you can see there is actually a structure that we can use by looking into the index. And therefore, this is what I want you guys to do. So the objective is that I want you to understand the details of the binary search tree, including all the functions, familiar with the link between the array and the binary search tree through the linked list implementation. The due date is going to be specified on the blackboard, and you have to work on your own work. Please do not look into your classmates' project or try to search online and copy paste the whole code from online. I did have some experiences that I found 4 students in my same class. They never talk to each other about the project. However, they submit the same projects without much differences. And I understand why is that. Please don't do that. Work on your own. This is actually not that difficult. So if we look into some examples, you can see that saying I'm going to create an array size of 10, then you will end up with these structures over here. Saying that I'm going to insert the node of 5, you have to see the special case scenario indicating that, okay, we don't have the elements at all, so it's actually an empty situation. So you will put 5 on the root. After that, if we try to insert one more element of 8, you will do the following things. Since this tree is not null, and try to map that concept with the linked list implementation code that we have done in the lab. Compare 8 with 5, we will search to the next location, finding this is a null node. That means 8 is supposed to be in this location. So you will put 8 in that spot, and therefore you will end up with a tree looks like this. If we try to insert another element 11, you will look into the root, go to the right side, finding it's not null, so you compare that, go to the right side, finding this is a null location, and you will insert 11 in here. So that is the idea of the binary search tree for the insert operation. Later, we will look into the requirements of each functions I want you to develop. There is one function called print binary search tree, which means I want you to print it out the whole binary search tree that you have. Of course, it is probably not a good idea to print it out the whole array you created. So if you see if the print function is called on this binary search tree, what you will print it out is that I want you to print out the index that holds the value. So index 1 holds the value of 5. Index 2 has nothing, so we don't need to output that. For index 3, it has a value of 8, so we will output that. 4, 5, and 6 has nothing over there, so we don't need to print it. Index 7 has a value of 11. That is the output I want you guys to generate from the print binary search tree function. Based on the example I provide you, you need to understand one thing. In our project, we will end up with insert 10 values. Those 10 values are given. However, your code needs to be able to handle whatever 10 values that's given to you. And therefore, I want you to think about this carefully. You see that we have 3 elements being inserted in here. And of course, our array is able to handle those 3 values. What is the worst case scenario can happen for this kind of implementation? And when that happens, what is your array size need to be able to handle 10 elements that's given in the worst case scenario? And that indicates when you try to define your one-dimensional array for the implementation, you need to specify the capacity that can handle the worst case scenario for 10 elements. This is an important thing for you guys to think, and as well as for you guys to implement in your code. So let's take a look of the detailed descriptions. So for the detailed descriptions, I want you guys to do the following functions. First of all, search function. So I want you to find the index that stores the element of x. So saying that, if we go back to the example, saying that I want you guys to search 11. So you will need to go through the path, finding out 11 is stored at index of 7. And 7 is the index output that I'm requiring you guys to do. So find out the index that stores X using binary search tree mechanism. And I also want you to print it out all the elements in the search path. So you need to show all the path and specify the index where that stores it. Finding the minima and finding the maximum using the property of binary search tree. Please do not write the for loop to look into the array and then try to find the minimum or maximum. Don't do that. Use the property of the binary search tree, means that you start searching from the roots and then keep going to the left side until you find nothing, and that indicating that node is going to be your minimum, and the same thing for the maximum. Okay. Print binary search tree is the one that I have specified earlier. Print out a binary structure in the form of array with index. And if that index has null value, then you don't need to output that. Finally, insert operation. So you also need to be able to implement the insert. Try to find the right spot, put the values into the binary search tree. So those 5 functions are the basic functions I want you guys to implement. Delete function requires a little bit of effort. Of course, delete has 3 scenarios. Case 1 is easy. Case 2, which means you want to delete a node that has 1 child, that is actually the most complicated one. Try to work on that one, because if you finish that one, case number 3 is a piece of cake. You can call the functions of your case 1 and case 2. And therefore, I put that as the bonus projects over here. If you do this one correctly, then you will be able to receive 2 credits on overall score. So again, it's 2 overall score, so it's actually worth a lot. It was time for you guys to dig in and then think about how is that going to be implemented. Again, because this is not a regular linked list implementation for the delete operation. If this is a linked list implementation, we see this one. It's not that difficult. However, this is an array implementation. It's not exactly designed for the delete operation, so it's requires a little bit more efforts. And that's why it's in the bonus project. Saying that you have finished all of those functions, what you will need to do in your main function is the following things. First of all, insert those 10 elements one by one. So your binary search tree will have 5 at the root, 8 at the right side of the root, 3 at the left side of the root, etc. So you will insert all of these items according to this order. Perform the binary search tree printed out function. So you will print it out the whole tree, indicating what it looks like. Perform the finding maximum, perform the finding minimum, and then perform 3 search operations. So these are the basic requirements for the project number 3. For the delete operation, if you are doing a delete operation, you will add those 5 delete operations into your main function. Like I said, these 10 values are given over here. However, your code needs to be able to handle all kinds of random values, and to satisfy that, you need to pay extra attention when you try to define your array size. So what you need to submit, including the output, take a screenshot of your output, and I also need a source code of your program. And that is what I want you guys to do for project number 3.